We'd like to welcome everybody to our webinar on characterization of unsaturated mine waste, a case history. Dr. Peter Robertson is going to be the presenter today. The webinar will last about an hour, and then we will finish with some questions. If you do have questions during the webinar, feel free to use the question feature in the GoToWebinar panel. We have also uploaded a PDF of the slides under the handouts in that same panel, which you can download for your own use. And after the webinar, it will be recorded and uploaded to YouTube. Give us a day or so for that to be available. And tomorrow you also receive an email thanking you for attending, and it can be used for your professional development credit. Thank you very much, and here is Dr. Robertson.
Thank you, Kelly. Well, welcome everybody. In this webinar, we're now going to start a series of webinars where I'll try to pick some case histories. And this first one is a project that I worked on that dealt with mine waste that were unsaturated, as you'll see, and some of the lessons we learned from that. And it actually resulted in a paper, and the paper is just being published in the Canadian Geotechnical Journal, and I'll give you the reference on the last slide. And in a way, the publishing of that paper triggered the idea of let's make a webinar out of it so that we can discuss it a little bit more broadly. Okay, how do I get the slides to go? Okay, it's not working. Okay, whoop, there we go, bear with me. Okay, this is just a reminder that we have our CPT guide. You can download it from a variety of websites, the Gregg site, my site, as well as the Geologismic software site. And of course, at the Gregg website are the other webinars too. So much of the background material is in the guide. Obviously, the guide doesn't cover this case history, but it does give you the background information. So the background on this particular project is that it's now becoming more common in parts of the world to stack either crushed or filtered mine waste in a moist state, and these are getting pretty big. They're over 100 meters high in some cases, and the stacking is often done where there's very little compaction. So although the material is moist, it's not placed wet, it is placed in a rather loose state, and so the resulting deposits are typically loose, and some of these areas are high seismic areas, and so one of the big design issues is liquefaction. And certainly one of the design challenges is that, is there a risk of flow liquefaction? Could the material actually experience some strength loss if triggered by an earthquake? So this is a case history where we're going to illustrate some of the challenges of characterizing this, this sort of mine waste material. And so this particular case history, it's a filtered mine waste placed for our conveyor and radial arm stacker with surface irrigation. Some of these mines, the way they actually extract the ore is actually through surface irrigation with certain chemicals. I'm not sure this particular project did that, but the point being is it's placed moist and there is fluid that's sprayed across the top. So fluid is actually placed into it, so there is a risk of it becoming saturated. And it's placed, in this particular case, it's placed in very large lifts, 20 to 30 meter thicknesses. They're not always that thick, but some are. The overall slope of this particular one was roughly 4:1, and it had 50-meter wide benches, and each of the individual benches was as steep as 2:1. So even those 2:1s, they are 20 meters high or so. The current maximum height of this particular one is 200 meters, and there's approximately 100 million tons of waste, and it's in a region of low precipitation and high evaporations. It's in South America. As is often the case, I can't actually tell you the actual mine or the actual location. I can just let you know that it's somewhere in South America. And here's an example of what radial stackers look like. This is not from the project. These are just internet images, so you can get some idea of what these stackers look like. So a conveyor system with a radial arm stacker at the end. Sorry, let me go back. And so you can see how the material is crushed and filtered waste, and then it's carried by a conveyor and then comes off the end of the conveyor belt on this radial arm stacker. And the radial arm, of course, rotates in the radial manner and places the material. And you can see why it's falling and therefore not overly compacted. Here's a quick cross section. You can see the maximum height is about 200 meters, and so the maximum thickness, the natural ground slopes up in the valley, so the thickness is about 110 meters and the total height's about 200 meters. I'm just going to talk about a recent site investigation at this site. They did 12 seismic CPTs with pore pressure measurements and dissipation tests. They measured both shear wave velocities and P wave velocities, and they installed about 23 piezometers at 6 locations, so they had nested piezometer locations, generally close to where the CPTs were done. They also did some drilling, some SPT, and some sampling, tried to get undisturbed samples as well as bulk samples, and they also did a bit of MASW at some locations, mostly near the toe regions in one, but there was some confirmation of the shear wave velocities. And they did dissipation tests, and here's just an example. This is one at 63 meters depth, so it's a long way down. And you can see that the pore pressure rises a little bit and then begins to decay. This is against log time, so pore pressure against log time. And you can see it decays almost to 100% equilibrium. But equilibrium's down at only about 30 kPa, so it's only 3 meters of head down at a depth of 63 meters. Many of the dissipations actually went to zero or very close to zero. Most of them were rapid. Nearly all of them had T50s less than 60 seconds, and that was a number that I had suggested, and then others have actually done numerical work to show that that's a reasonable number, that when T50 is less than about 60 seconds, then typically you're into partial drainage. It's not a fully undrained penetration. Of course, it's also not a drained penetration. It's partially drained. And you see it in reflected that there is some excess pore pressure during penetration and they dissipate down. And remember, the fluid is coming from the irrigation at the surface as it filters down through it. So here's a typical CPT. It's the one at the highest section. So it's pretty impressive. This is 96 meters deep. So it's pretty impressive that they're able to push CPT through this material. If you look at the cone profile quite carefully, you can roughly see sort of 20 to 30 meter lifts. You often see a little drop in the cone resistance, maybe where the lift boundary was. Here from about 34 down to 46 meters is probably one of the lifts, and then a slight drop. And you also tend to see that where that drop occurs at the boundary between different lifts, you tend to see a little spike in the measured pore pressure during cone penetration. And so that may be where there's some fines accumulate at the end of the lift due to maybe some trafficking of material as well as erosion, etc., that creates a fine covering on top of the lift, and then of course that's reflected in a slight buildup of pore pressure when the cone pushes through. And also notice I've shown a dashed line that would show the hydrostatic line if the water table was at the ground surface and it was hydrostatic, and you can see a number of dissipation tests are identified here, and all of them dropping down pretty well close to zero. The solid blue line shows a simplified linear equilibrium with a very small head down at sort of 100 meters depth. The excess head down at 100 meters is less than 50 kPa. So in terms of calculating total and effective stress, it's using the total unit weight subtracting this equilibrium pore pressure, where the equilibrium pore pressure is a very small value, close to zero. So assuming no suctions, we'll get to that issue a little bit later. And so here's the normalized profile. So you've got normalized cone resistance, normalized friction ratio, BQ, and then the normalized soil behavior type. And you notice I've got, because it's almost 100 meters high and pore pressures are very low, it's not hydrostatic, so the vertical effective stress is very high. It's approximately 15 atmospheres down there. So you've got very high overburden pressures down at the bottom of the stack. So this is what the data looks like if you plot it on the normalized soil behavior type. This is the original sort of the 1990 normalized chart that I updated in 2009. The update in 2009 was just sort of updating the normalization procedure. And you can see that I've sort of removed the upper 20 meters, so I'm focusing on from 20 meters down to 90 meters, and just to sort of remove this little tail ends near the surface. And most of the data falls into zone 4, which is sort of the silty clay, where IC is a little bit larger than 2.6. And this is assuming no suction, so it's based on that effective stress that we showed before. And then here's the updated chart. Some of you have been watching the webinars. I published a paper last year in the Canadian Geotechnical Journal to give a slight update to the soil behavior type, giving a sort of like slightly more hyperbolic boundaries to capture the response a little bit better over the region, and also putting in a boundary that separates dilative from contractive behavior. And you can see that most of the data plots slightly on the contractive side. There is some on the dilative side, and most of it falls into the region that we would refer to as transitional behavior. So to the left here, you've got sand-like dilative and sand-like and contractive, and then you've got clay-like dilative and clay-like contractive, and then clay-like contractive and sensitive, and then the green zone is transitional material that transitions from sand-like to clay-like, and that's where most of this data plots, and it's mostly on the slightly contractive side. And here is that updated value. So here's this updated soil behavior type index IB, and you can see most of it's falling in that transitional zone. And if you look at the descriptions, most of it's described as transitional or clay-like and contractive. So once you're below the upper 20 meters or so, it's mostly on the contractive side. Now, for the seismic measurements, a little bit of background here. So in terms of shear wave velocity is controlled by the in situ effective stresses, the void ratio, and age and cementation. Now, of course, this is a tailing, so the age is very young and there's essentially no cementation. So shear wave velocity is controlled mostly by effective stresses and void ratio, whereas the P wave velocity, the compression wave, is controlled mostly by degree of saturation. And we know that the P wave velocity is about 1,500 meters per second, or roughly 5,500 feet per second in saturated soil. And then there's a very sharp drop off. So when you go from 100% saturation down to 99% saturation, the P wave velocity will drop from up around 1,500 meters per second and drop sort of down around 500 meters per second or less. So ironically, you don't have to measure P wave velocity super accurate to be able to distinguish saturation, because it drops off so rapidly in softer soils. Of course, in rocks, where rocks are very hard, then P wave velocity can be larger than 1,500 meters per second, and that's why P wave velocity is more sort of commonly used in rocks and less so in soils. And if it is used in soils, it's used mostly to determine where saturation is. So that's a little bit of background. Here's the actual measurements from that 96-meter seismic CPT. So shear wave velocities, started off around 250 meters per second and then increase with depth, of course, because of the confining pressure, and eventually get up to around 500 meters per second. And the P wave velocities start off at around 400 or 500 meters per second, then eventually rise up to maybe as high as 1,000 meters per second, but significantly less than the 1,500 meters per second. So indicating that it's predominantly unsaturated material. And on the right-hand side, I'm showing the normalized shear wave velocity, VS1. And normalized shear wave velocity is where it's the measured shear wave velocity, and then it's normalized with the overburden pressure, where it's atmospheric pressure divided by vertical effective stress to the power of 0.25. And if I show what the average value is, the normalized shear wave velocity average is around 225 meters per second, plus or minus a bit. Now, back in '95, I had suggested, and that's generally supported by more updated information, that the boundary between contractive and dilative behavior in terms of shear wave velocity, normalized shear wave velocity, is a normalized shear wave velocity of somewhere around 150 to 170 meters per second. I'm showing it roughly at 170 here to be conservative. And you can see that all of them normalized measured shear wave velocities are larger than that value, indicating that based on shear wave velocity, the material would be considered dilative. So, in terms of in situ test interpretation, the CPT-based interpretation would suggest that the soils are mostly contractive at large strains, but the shear wave velocity based interpretation would suggest that the soils are predominantly dilative at large strains. So the challenge here is, well, which one's correct, or are they both correct? And that's what the project really delved into, and we were fortunate to have a group of people that were willing to do some additional testing to evaluate this further. And so a little bit of background, the index testing on the soils, it's a relatively uniform grain size distribution. It's predominantly sandy sill, probably gets finer with depth because of the high overburden pressure and crushing and a little bit of weathering. And the fines content is typically around 50%, higher in places, it's not uniform, but on average around 50%, a little bit larger with depth. Mean grain size is about 0.065 millimeters. Specific gravity is not exceptionally high, just a little bit high at 2.73. It's mostly non-plastic. There are some regions where it's a little bit of plasticity, but generally non-plastic. The in-situ water content varies from about 2% to 15%, depending on depth and location and whether or not they were irrigating close by at the time. So the degree of saturation varies from about 5 to 50%. So certainly it's unsaturated. That's confirmed by the compression wave velocity measurements. So we did some lab testing, and as I say, we were fortunate that the people involved in the project were able to do some lab testing. And we were fortunate that we were able to send samples, these are bulk samples, to a lab in Portugal. So Professor Antonio Divan Fonseca did the lab testing in Portugal because he had the ability to do lab testing and measure both shear wave velocity and P wave velocity on samples while they were being consolidated and while they were being sheared. So we did a series of tests on saturated reconstituted samples. So we got a bulk sample that we considered to be reasonably representative. Unfortunately, because it's a mine waste, it was relatively consistent. And so we reconstituted samples to very loose conditions so we could determine critical state parameters. And then we measured both the shear wave velocity and P wave velocities on those reconstituted samples. And so we were able to measure the link between shear wave velocity and the stress on the sample. So we normalized the stress out and then get the relationship between the normalized shear wave velocity and void ratio. I'll show you that in a moment. And then we also were able to do some tests, and this was really with the help of Antonio, where he had a grad student or a number of graduate students that actually did some additional tests on unsaturated reconstituted samples. So the same reconstituted material, but we sort of duplicated them, made them very loose, but kept them unsaturated. So first we determined the relationship between suction and degree of saturation or water content, so the soil water characteristic curve, which I'll talk about briefly. And then we were able to measure the influence of suction on the behavior. And then also we were able to measure both the shear wave velocity and compression wave velocities on those unsaturated samples at known suction levels, and then compare those with our field measurements. So that's the sort of background of what we did. Now let's have a look. A little bit of framework. So, we wanted to determine critical state parameters. So a little bit of back on the framework. So background, we know that for clay-like soils, clays generally have a single normal consolidation line. So you've got this line in terms of void ratio against log of mean normal stress. And so and you've got this critical state line. So for normally consolidated clays, they're on the contractive or the wet side of critical state. So if you were to shear them undrained, they would have a buildup of positive pore pressure as they move towards critical state, so the effective stress would drop. Or if you tested them drain, they would contract to critical state. And that spacing ratio between the normal consolidated line and the critical state line, they're basically parallel. It's typically between 2 or 4, and we know that, for example, when you have a clay that has an OCR of 1, it's on the normal consolidation line, and when it has an OCR of about 4, it's pretty close to the critical state line, and when OCR is greater than 4, then you're over on the dry or dilated side. So that's what we know from sort of critical state soil mechanics for clay-like soils. And for sand-like soils, it's sort of similar. You've got a critical state line, generically shown here. And the big difference for sands is that they don't have a single normal consolidation line. You can actually make sands to a range of different void ratios and stress. So in a sense, they have an infinite number of consolidation lines. And so, of course, if you have a sand that's relatively loose, it may initially be on the dilative side, but as you consolidate it down, and so the void ratio does decrease, it gets denser, but it begins to cross the critical state line, and so it does tend to become more contractive with increasing stress. And several researchers have suggested that there's actually a limiting compression curve, and this is actually built into the MIT sand model that Professor Andrew Whittle and his colleagues have worked on. And so they've suggested that there is, in fact, a limiting compression curve for sands, and in fact, at high stresses, it's basically parallel to the critical state line, as I've shown. And it likewise has a spacing ratio of about 4. And when you come to sands in critical state, Bean and Jeffries devoted a lot of their career to helping us understand this and suggesting that the state parameter was one way to define state, and it's basically the void ratio difference between its current void ratio and the void ratio at the same mean effective stress at critical state. So that defines the state parameter. And of course, if it's positive, it's on the contractive side. If it's negative, it's on the dilative side. The alternative approach, which one could argue would be a little bit more consistent with traditional practice of clays, where clays we talk about an OCR, which is the stress ratio. In sands, likewise, we could have defined state as this stress ratio, which is the ratio at that given void ratio at the same void ratio. So the mean normal stress at the void ratio and stress that you're at compared to the effective stress at critical state at that same void ratio. And up in the corner is the equation, and that stress ratio would be, if it's in log to the base 10, it would be 10 to the power of the state parameter divided by the slope of the critical state line. And of course, if the critical state line is curved, it would be the slope over that range of stress. So a little bit of background. I'd like to maybe just pause for a second here. You notice I'm referencing Bean and Jeffries' work here. And Ken Bean passed away just 3 weeks ago. So it was a great loss to our community that Ken should pass away at really such a young age. But his contribution continues. I mean, he's published some of these seminal works, this one here referenced in '85, about state parameter for sands. And of course, he published the book with Mike Jeffries on soil liquefaction, a critical state approach. And so, much of his contributions will live on. So if we actually get back to the data for this particular project, this sandy silt tailings. So here's a summary of the critical state line on the saturated sample. So what we did is we made samples very loose, void ratio in excess of 1, and then consolidated it down, and then at various stress levels, and of course therefore various void ratios, tested them either undrained or drained. And so I've marked in roughly the loosest compression curve. It's probably not exactly right, but it won't be far off. And then I've identified the data points that define the critical state line. And you can see that for the very loose samples up around a void ratio of 0.8, the ones that were tested undrained lost all their strength. So the stress path moved to the left, and the mean effective stress went below 1, so it essentially lost all their strength. And then as they got a little bit denser, they then eventually did have some strength, and then at higher stresses, they still were contractive, but they weren't losing quite so much strength. And so that's a summary of the tests we did on the saturated reconstituted samples. And because we're going to talk about strength loss, we could talk about sensitivity to define that, but Bishop back in '67 had suggested defining it in terms of brittleness. And brittleness was the loss of strength divided by the peak strength. Sensitivity, of course, would be the peak strength divided by the remolded strength. And so here it's the loss of strength. The nice thing about using brittleness, of course, it goes from a value of 0 to 1. So if it's got a value of 1, that means there's 100% strength loss. And if the value is 0, there's no strength loss. And so when you think about those tests I just showed, these very loose samples that lost all their strength had a brittleness of essentially 1 or very close to 1 within their ability to measure that. And so we can look at brittleness against state parameter, and Bean and Jeffries here in their book, they correctly sort of said that rather than just state parameter, it should be state parameter divided by the slope of the critical state line. Here it's in terms of log to the base e with the data they show. And this is directly from their book. I've just drawn an approximate line through there to illustrate the relationship. There's quite a bit of scatter, and you'll see why that may be in a moment. But in general, you can see that when the value of the state parameter gets very large, the brittleness goes essentially towards 1, and then eventually at low state parameters, it then comes down to essentially 0 brittleness. Now, Sadar-Karimi and Olson from the University of Illinois published a very nice paper in the Canadian Geotechnical Journal, where they looked at data from a number of different sands. And instead of plotting it against state parameter, they chose to plot it against this stress ratio. And you can see that they get much less scatter. And one could argue that the problem when you use state parameter and the slope of the critical state line is if the critical state line has some uncertainty to it, or if it's got some curvature to it, getting the slope is actually quite difficult, whereas the stress ratio is a little bit easier. And you can see that they're getting the same relationship, very high brittleness for these large stress ratios, and then as the stress ratio becomes smaller and smaller, the brittleness begins to disappear. And so if we go back to the curve, you can actually, the critical state line on the saturated samples, we can define regions on here that says, yes, at this very loose state, if you're on the contractive side of the critical state, you're essentially contractive and brittle, and they can be virtually complete loss, so almost a brittleness of 1. And then you get into a region where it's still contractive and it's brittle, but there's less strength loss. And then eventually, when you get to where the limiting or the loosest compression line is essentially parallel to the critical state line, it's still contractive, but it's more ductile. There's much less strength loss. The brittleness, brittleness index now is sort of a much smaller amount, so it's not losing as much. So at higher stresses, the material can be contractive, but it tends to be more ductile. It's at the very low stresses that when it's contractive, it tends to be more brittle. I'm giving a presentation at a conference in Vancouver next month, and in fact our next webinar will be on this topic of the influence of high stresses. So the next webinar will go into this in a little bit more detail. So we measured shear wave velocities, and if you normalize the shear wave velocities with the effective overburden stress, and of course these are saturated samples, so there's no suction, so it's pretty straightforward using that equation I showed you before for the normalization of shear wave velocity. And so you get normalized shear wave velocity against void ratio, and you get a reasonably consistent relationship. This is, we originally suggested this back in about 1995 with John Cunning as a graduate student, and there was a paper in the Canadian Geotechnical Journal that sort of outlined this approach of normalized shear wave velocity against void ratio. And here's the equation. And this equation is the same format that John Cunning had suggested, just the constants are changed a little bit. Another way to look at this, before I do that, if we actually put on the the field shear wave velocity, the normalized value of 225 meters per second, and follow that relationship up, it would suggest that the in situ void ratio would be very low, down around 0.2, so that seems a bit strange. But of course, these are saturated samples, and of course in the field, it's not saturated, so we'll address that issue. An alternative way to look at this is you can look at the critical state line, and you can draw, with that equation, you can draw contours of shear wave velocity. So these are contours of measured shear wave velocities, not normalized. And so, for example, at a mean normal stress of 100 here, you can see that the measured shear wave velocity crosses it at a little over 125 meters per second when the void ratio is somewhere between 0.6 and 0.65. So if I go back to the previous one, here's the values here. This would be roughly where you're at critical state. These would all be looser, and these would all be denser than critical state. So you can see that for this particular material, it would suggest that a normalized shear wave velocity of about 130 meters per second would be that boundary between contractive and dilative behavior. And if you, the work by Bean and Jeffries has suggested that it's not exactly right at a state parameter of 0, it would be slightly on the negative side. So one could argue it's a little bit closer to 0.6, so it's closer to 130, 135 meters per second. But a number much smaller than the actual field values. So we did tests on unsaturated soils. So a little bit of background on unsaturated soils. That means the voids are filled with a mixture of fluid and air that results in suction. And the suction can be represented by a soil water characteristic curve, this SWCC, and this defines the relationship between the soil matrix suction, which is the air pressure minus the water pressure, and the degree of saturation. So here's an ideal. I took this from Louet and Height, their excellent paper in 2003, which was an excellent review paper if ever you want to read a paper that sort of summarizes a lot of things about soil behavior. So they had a section on unsaturated soils, and they show an idealized soil water characteristic curve. And in simple terms, what it means is that when you're at 100% saturation, as you apply some suction, you eventually reach a air entry value where air would break in. Of course, it's slightly curved in the capillary saturation zone. And then as suction increases, of course, degree of saturation will decrease quite rapidly. And then you get into this zone of residual saturation, and there's this residual water content. And then at residual saturation, it declines at a slightly lower rate. And so here's the measured soil water characteristic curve. These tests are actually quite time consuming, and Antonio did an excellent job to collect this data. You can see the values are very low. We're starting at about 4 kPa, so that's about at the limit of the testing equipment. Hence, the projection to 100% saturation is estimated because it's beyond the accuracy of the testing equipment. But within the range of the testing equipment, you can see that at 40% saturation, you've got about 4 or 5 kPa suction, and then as the degree of saturation drops down to about 10 to 5%, you're up at about 200 to 300 kPa of suction. So not very large suctions in the field. And here it is plotted against water content. So the range for the projected tailings is somewhere, from about 4 to 300 kPa, and on average around maybe 100 kPa in the field. And so in Louet and Height's paper, they show sort of typical examples of soil water characteristic curves for a range of soils. And if I sort of show where our project sandy silt filled, it does sort of plot closer to their sand example. So the sections are relatively small. And when we talk about what influence this has on the effective stress, there's this well-known equation that the effective stress is actually the total stress, which is the total stress minus the air pressure, plus some factor into the suction, which is the air pressure minus the water pressure. And here it is simplified down. Really, it's just the total stress plus the suction times this chi factor. And this chi factor varies from 1 for saturated to 0 for dry. And it's often, there are a number of relationships, but often it's assumed that this chi factor can be approximated to the degree of saturation. So it varies from 1 to 0. So at a saturation of about 10, then this chi factor would be about 0.1. So you're going to add on 10% of the suction. And so if the suction is only about 100 kPa, then you're only going to add on about 10 kPa. So, in these sort of sandy soils, the suctions are typically small, and so their effect on effective stress is relatively small. Now, of course, they're significant very close to the surface. So where the total stress may only be, 20 or 30 kPa very close to the surface, then when you add on 10 kPa, that can be a significant addition. But once you're 20, 30 meters down in this stack, the total overburden pressure is very high, and then the addition of the suction is very small. And so we see that, generally at depth, the effect of suction is minor in terms of the effective stress. But there are other effects that suction brings about, and one of them is that researchers have shown that the size of the yield surface grows with suction, and they often refer to this as suction hardening. And so soils tend to behave more like over-consolidated soils due to the suction, due to the size of the yield surface increasing as a function of suction. So we're going to come back to this suction hardening effect a little bit later, because that is potentially more significant than the actual direct effect on effective stresses. And also the critical state line also appears to move as a function of the amount of suction, and that the amount it moves appears to be dependent on the type of soil. So this apparent cohesion, as the sometimes referred to as an apparent cohesion intercept, as the movement of the critical state line. So here's an example again from Louet and Height. They show this example of a compacted silt, and you can see that the extensive lab testing at a range of different suctions, and you see the yield surface grows in size as more and more suction is there. So on our project, what's the influence of suction? So in unsaturated soils, they tend to be more compressible because, of course, the soils have now got air in the voids. So when you're pushing the cone in, generally the materials are more compressible, so they will tend to give lower cone resistances due to that increased compressibility. But of course, that's a function of if it's drained or undrained. Of course, if it's a drained penetration, it wouldn't make any difference. It would only make a difference if it's drained, and we saw that the penetration was sort of in that partially drained region towards drain, so not a huge effect likely. But the compression that occurs around the face of the cone tends to actually increase the suction, increase the degree of saturation around the face of the cone as the cone is being pushed in, which partly explains why we're able to measure some positive pore pressures during the CPT, even though the material is not 100% saturated. So the compression that's occurring in front of the cone is actually compressing the voids and therefore pushing the material closer to 100% saturation. So during penetration, it is possible to measure relatively larger positive pore pressures, even though the material may not be 100% saturated. And as I said before, the change in effective stress appears to be small. So if saturation is on average around 10%, so this chi factor is around 0.1. So at a depth greater than about 20 meters or so, where the overburden pressure is about 500 kPa, adding on 10 kPa is a very small effect. It's just 1 or 2% change in the calculated effective stress. But suction hardening does tend to make the material more stiff at small strains. And so that may explain what we're seeing in the shear wave velocity. So Antonio did a series of additional tests where he made samples that were unsaturated at known suctions and then measured the shear wave velocity. So here's this plot of normalized shear wave velocity. So here I'm normalizing it based on effective stress. So if it's unsaturated, I'm accounting for the suction because we know what the suction is. So I'm making a small adjustment for that known suction. And so here's the line that we got for the saturated samples where suction was 0. And he did a series of tests at 20%, sorry, not 20, at 20 kPa applied suction, and one that was very loose. The others were a little bit denser. And these 4 tests initially at about 50 kPa and then eventually down to 600 kPa. And so although there was this very large change in total stress, the normalized cone resistance didn't change much. It was basically around 200 meters per second over that very large change in total stress because of the compression of the material, the void ratio changes, etc. And then he did 3 tests at 200 kPa suction, and again 3 from a range of 50 kPa up to 600 kPa, and again essentially the results were all around 210 to 220 meters per second. So this relationship appears to change significantly with applied suction. So here it is down where the suction is 0 and it's saturated, and maybe 130 meters per second for the boundary between dilative and contractive. But when you apply some suction, the suction hardening, not the effect of effective stress, but the suction hardening pushes it significantly up from like 120 up to 220. So almost doubling of the measured shear wave velocity. And remember, the small strain shear modulus is the shear wave velocity squared. So a doubling of the shear wave velocity is 4 times increase in the small strain shear modulus. And then if I actually add on the in situ range, so the range of in situ measured normalized shear wave velocity was, on average it was about 225 meters per second, so it ranges from roughly 200 to 250 meters per second, and the suctions are probably, in the range of about 20 to 200, on average about 100 kPa suction. So I've sort of drawn a zone and said, well, this is likely where the in situ values are in terms of both suction and shear wave velocity, and that means that the in situ void ratio is probably in the range of 0.6 to 0.7. Obviously, as you go deeper, it's probably closer to the 0.6, and it's shallower, it's closer to the 0.7 because of the overburden pressure. But at least now we've got a range of where we think that in situ void ratio is. And if we now go back to the critical state line, so here's the plotted on a slightly different scale now. So here's the critical state line for the saturated samples and the loosest compression line. So remember, the samples were prepared very loose, and you can see there's quite a lot of compression when you saturate the sample. So up around 1.1 void ratio, and then dropping below 0.9 when you saturate it. So there's the loosest compression line for the saturated. Now if I add in the approximate loosest line that we were able to make for our moist samples using a moisture content similar to the average moisture content in the field, you can see now, of course, we're not getting that loss of void ratio because we're not saturating the samples. And now if I add on the test results where we were able to determine the critical state line for unsaturated samples at different suctions. I'm only showing the 4 data points for the 200 kPa suction, but there was also data for 20 kPa suction. You can see there's not a lot of difference between the critical state line of these moist samples for those different suctions, but it is significantly different from the saturated samples. Now if I put on the project estimated in situ void ratio range, remember it was roughly from about 0.6 to 0.7, I've extended it down to about 0.55, and this is the stress range, mean effective stress from about 1 atmosphere to 10 atmospheres, and actually I've got it as high as 15 atmospheres. You can see that in terms of the saturated critical state line, it's slightly on the contractive side, but in terms of the unsaturated critical state line, it's on the dilative side. So maybe this makes sense now that the shear wave velocity appears to be sensitive to suction hardening since it's a small strain measurement, and so it's more sensitive to that little bit of hardening that occurs at small strains due to the suction hardening, not the actual suctions themselves, that influences the effective stress, but the actual hardening that occurs. And so that the shear wave velocity appears to be a better indicator of the unsaturated behavior, correctly predicting that it's predominantly dilative in the unsaturated region. And then the cone resistance, because it's a large strain measurement, appears to destroy these beneficial effects of the suction hardening. And so the cone resistance maybe a better indicator of the behavior of the soil if it were to become saturated and if this suction hardening gets destroyed due to the saturation effect. So in a sense, maybe they're both right. Shear wave velocity is giving you a better indicator of the behavior in its unsaturated behavior, and in this particular case saying it looks like it's predominantly dilative at large strains, and the cone resistance is saying, look, if the material were to become saturated, it could become slightly on the contractive side on this particular project. So in summary, the seismic CPT provided valuable data in this particular one, a continuous profile down to 100 meters. And so, I'll just take a moment here that I know Gregg sponsors these webinars. This was not Gregg CPT data. It was actually Context data from South America. So I congratulate them to do such nice quality seismic CPT data down to almost 100 meters and collect both shear wave velocity and P wave velocity data. And dissipation tests were carried out, lots of them, and they confirmed the piezometric profile, a strong downward flow, significantly less than hydrostatic, supporting that it's predominantly unsaturated, which is supported by the P wave velocity measurements. So a strong downward flow resulting in very high vertical effective stresses at depth, and shear wave velocity appears to be helpful in identifying the benefits of this suction hardening, and the P wave velocity was helpful in identifying the lack of and confirming the lack of saturation. And so suction can have an added influence on the behavior due to this suction hardening beyond just the actual effective stress, because this is a sort of a relatively sandy material, and so the suctions are not overly large. And so once you're below the upper 5 meters or so, then the change in effective stress due to those suctions are pretty minor, but the influence of suction hardening can be significant. So that concludes this sort of case history, and here's the acknowledgement. So my colleagues that I worked on, Antonio da Fonseca from Portugal, from the university in Porto, beautiful town to visit if you want to go there, and then Brian Ulrich and Jeff Coffin from Knight Piésold. And I acknowledge and appreciate the support that they gave that enabled us to do the lab testing, and then Antonio doing the additional lab testing on the unsaturated to sort of close out our understanding of the behavior. Just the one question. Okay. Well, if you're dreaming up stuff to ask, then go ahead and type it in. But the one that came in, it says, can you compare shear wave velocity from, okay. I didn't show the slide. I do mention it in the paper that's referenced here in the Canadian Journal, is they only did MASW in a small region down near the toe of the stack. And so there wasn't a lot of overlap between the seismic CPT and the MASW, but where there was overlap, the MASW confirmed basically the same values that were measured from the seismic CPT. Obviously the depth was shallower because it was in the toe region. But yes, the MASW worked. Now, obviously doing MASW down to 100 meters is going to be challenging. You have to lay out the geophones to a very large extent. It's possible to do. The interpretation gets a little bit more approximate as you go deeper and deeper with surface waves, because you have to go to very low wavelengths. So it's pushing it a little bit to go to 100 meters. But even the seismic CPT, it's certainly the deeper you go to, downhole seismic becomes a little bit more challenging. And you saw that reflected a little bit if you saw the scatter in both shear wave velocity and P wave did increase with depth due to slightly decreased inaccuracy in a downhole seismic method when you go to these significant depths. Another question was, how reliable are dissipation tests in unsaturated mine waste? Okay, that's a good question. There was a very nice paper in, I believe it was ASCE in 2012 by Jason DeJong out of UC Davis and Mark Randolph. And they did a very nice paper looking at the theory of dissipation tests and extending it into the region of partial drainage, and showing that the relationship between the time for dissipation, such as T50, and the coefficient of consolidation becomes sort of no longer unique. In other words, the relationship is no longer a nice linear relationship. It curves over. And so for one value of T50, there's large amount of uncertainty in the coefficient of consolidation. In terms of the basic shape of the dissipation, I mean, you saw from the curve, the dissipation curves, look pretty good. They had the basic shape one would expect. I'm going back to it here. You may be asking, how reliable is, for example, the equilibrium? And when I did the webinar on dissipation tests, and one of the comments I made is one of the nice things about dissipation tests is, although it may not start off saturated, it does tend to move towards saturation with time. And it is going to a positive value. I mean, in this particular case, it's only 3 meters or 30 kPa, but it is heading towards a positive value, which means it is close to being saturated around the cone. Obviously not going to be perfect, but they did install, if you remember, they did install 23 electronic vibrating wire piezometers in 6 nested locations. And the piezometers, here they are, yeah, 23 piezometers at 6 locations. And they did confirm the general equilibrium pore pressures that the CPT got. I have been involved in other cases where the CPT, in a bit like this curve, it didn't get to 100% equilibrium, so there's a little bit of uncertainty about where equilibrium was. And I have been involved in a project where the piezometers that were installed and therefore monitored over much, much longer periods went to even lower pressures. So here we're sort of showing 3 meters head of water at 63 meters depth. It is possible that the piezometers would have gone slightly lower than that, but in terms of the overall interpretation, it wouldn't have affected what we did for interpretation. Now you're pressing my memory. The next question is, what was the bulk density of the mine waste? That I can't remember, but I think we used, because it was placed loose, I think we used somewhere between 16 and 19 kilonewtons per cubic meter. The overall interpretation and calculation is not overly sensitive to that number. I know certainly we're going deeper, and so the normalization at depth will be influenced by the exact unit weight, because after all, you've got almost 100 meters of it there, so it does affect it a little bit. But we were using bulk densities, if I recall, on averaging around 17 or 18. I said 16 to 19. I do say in the paper what it is, and I can't recall exactly what it is off the top of my head. And then it says, what method was used to determine P and S wave velocity? So it was seismic CPT, and so this is a downhole method. So you push the cone in, and basically every meter you add another rod, and so during those pauses you can generate either a P wave or a compression wave at the surface. Now, either a compression wave or a shear wave at the surface. The shear wave is where you would hit a horizontal beam. By hitting it horizontally, you're generating a shear wave, and that would travel down to the geophone in the cone. And then if you just did that at one depth, that would give you the average shear wave velocity. But of course, if you repeat it every meter, then you actually get the interval velocity over that 1 meter. And so that's how they're able to actually, sorry, where is the curve? Right here. They're able to get all of those data points. So they're basically stopping every meter, and you can see there's lots of data points. And so they're able to determine the shear wave velocity every meter interval as they progress in the penetration. And with the P wave velocity, it's similar. It's a downhole method, but this time they're usually hitting something vertically. Sometimes it's a plate placed on the surface. Sometimes it might be a small auger installed into the shallow surface and then hit vertically, and so that generates a compression wave that travels down. And again, if you do it at one depth, you would get the average compression wave velocity, but of course if you repeat it every meter, then you get this what's referred to as the pseudo time interval as you calculate the velocity. And here you can see the scattering p-wave velocity does increase fairly significantly with depth. It's not perfectly accurate, but we're only looking at, is it less than 1500 meters per second, and it's clearly, you know, almost half that value. So although the p-wave velocity is not super accurate at depth, for the application we're applying it to, it doesn't have to be super accurate. So I think the next question is, what influence do you think chemical weathering due to acid irrigation would have on the structure of the soil and the resulting shear wave velocity and cone resistance? That's a good question, because a lot of these stacks, it's where chemicals are irrigated at the surface, and so, you know, they weather the material. And so what you essentially tend to find is that the material, this is material that would weather naturally. I mean, South America, for example, has a lot of residual soils, which are where the rock weathers in place due to rainfall and heat and humidity, etc. And so what you tend to find is acid irrigation, in a way, accelerates the weathering process. And so that, depending on what the parent rock is, depends on what happens during this accelerated weathering process. So instead of weathering in natural terms, possibly taking thousands of years or even millions of years, in this case, of course, it's highly accelerated. So the chemical acids tend to weather away the material, and so you get a decomposition. And so some of the material, as it decomposes, can become more clay-like. Now, it depends on what the parent rock is, of how much clay-like it will become. But certainly in some projects I've worked on, there's no doubt that the material is often placed actually in chunks of rock, which at first seem, how can you possibly push the CPT in this material? But what it is it's chunks of rock that are weathering quite rapidly. So there's a phrase used, agglomerated, where basically this rock weathers quite rapidly around its edges, and so it becomes more clay-like. And so not on this project, the material here tended to maintain that sort of sandy silt composition, you know, with a fairly uniform grain size, etc. But on other projects, the weathering has created, you know, when they do it in these layers, by the way it's stacked, it can create, the term I've used is that fines dominated and non-fines dominated regions. So where you've got significant weathering, where the parent rock was such that it breaks down and becomes more clay-like, you tend to see a more clay-rich deposit, and others less clay-rich, and so hence fines dominated and less fines dominated. So hopefully that answered that question. Are both saturated and unsaturated critical state line tests based on moist tamp samples? Yes. So all of the testing we did, we made samples as loose as we could using moist tamping. And the reason for that is we specifically wanted to, we wanted to determine this loosest compression line, because that in a sense creates a reference to the critical state line. And then also when you perform either the undrained test or the drain test on saturated samples, you often get a better definition of critical state when you're starting from these very loose states. And of course on the moist samples, one could argue they've got some fabric due to the way you made the samples. But remember, this material is placed moist, so the way we're placing it in the lab is mimicking reasonably well the way it's placed in the field. And then also, if we come back to that reference I showed back here about, you know, state parameter and brittleness, one of the key things here is that when you're at critical state, the critical state line is independent of fabric. And so, you know, because you're going to large strains to get to critical state. So the initial fabric doesn't play a role in actually defining the location of the critical state. And so here, this work that Sadrak Karimi and Olson did, I hope I'm pronouncing that right for him, is that the results are independent of the way they made the samples. And a number of researchers have shown this. So brittleness as a function of either state parameter or the stress ratio is independent of both direction of loading, whether or not it's compression or extension or fabric. And so that's an important observation to take note of. Next question. What do you think about the speed of penetration, its effect on saturation? Yeah, okay. So we sort of said that at the standard rate of penetration, one could argue that we had partial drainage during that standard rate of penetration, supported by these relatively rapid dissipation tests. Now, a school of thought would be, well, if you ran the test faster, could you have pushed it into the undrained region? And if you ran it slower, could you have pushed it into the drain region? And the answer is yes, that's probably true. But what we do know is that that region of partial drainage is basically 1 to 2 orders of magnitude. So with all other variables being constant, you would have to change the rate of penetration by probably about an order of magnitude. And so if you're pushing it 2 centimeters a second, that means either you've got to go at 20 meters a second to push it to undrained, or you've got to go to 0.2 centimeters per second, which is very slow. And so, from a practicality, you can do it in regions, but you can't do it overall. Remember, this was 100-meter sounding, so it's not very practical to do either one of those, either faster or slower. But yeah, we certainly could have picked a region and said, let's do what's often referred to as a twitch test, which is to change the rate and see how it changed the result. I personally don't think it would have changed it that much. And I don't think it would have changed the interpretation. So for example, if we had pushed it faster, pushed it into the undrained region, the cone resistance would have gone down a little bit. If we slowed it down, pushed it into the drain region, it would have gone up a little bit. If it had gone up a little bit, it may have pushed more of it into the dilative region. But keep in mind that that chart, that divides contractive from dilative on the soil behavior type chart is on a log scale. And so, the data point, to move a significant portion of it, there's a lot of the data, with a normalized cone resistance of, say, around 10, to push it up into the dilative region, it would have to go up to 30. So it would have to increase by a factor of 3. Now, if it's partially drained, it could go as high as 3, but, if you're already in the partially drained region, that means you're already partially up that curve. And of course, if it is dilative, a lot of the research on partial drainage is on soils that are contractive. And so, when you test it drained and then go to undrained, the drained value is typically 3 to 4 times larger than the undrained value, which is saying, yeah, this is a contractive material that if you test it undrained, it has an undrained strength about 1/3 of what the drain strength is. Very few people have done research on dilative material looking at the rate effect. But since we know dilative materials, the undrained strength could be larger than the drain strength, so partial drainage goes the other way around. So it's not exactly clear how big the effect is when the material might be on the boundary between being contractive and dilative at large strains. And so if it's on that boundary, it's sort of not much contractive, not much dilative, then in fact the changing the rate would have almost no effect in terms of drainage. Next question. Has anyone looked at predicting compressibility from CPT or shear wave velocity in partially saturated tailings? The answer is probably not. Many years ago, we did talk about predicting sort of compressibility in sands based on seismic CPT and saying that the relationship between the two could be used. And it's a good question. I think the answer is you probably could do it. And in fact, on this paper, this 2016 updated soil behavior type chart, there is the plot of G over QT against normalized cone resistance. And when you show the data plotted on that, it plots right in the normal region. So that, the partially saturated response, instead of getting significant microstructure, is plotting in the normal region, saying there's not much microstructure, and I suspect that's because of that increased compressibility. Now, whether or not you can actually get compressibility out of it, it probably could, and no one's actually done it, I don't think, but it's worth looking into. Next question, have you encountered tailings where lab testing indicate dilative or phase transformation response while CPT indicates contractive behavior? And the answer is yes, but the difficulty there is that typically when that happens, it's where people have done lab testing on, quote, undisturbed samples. And these are often Shelby tube samples, just regular thin-walled tube samples. And so the risk there in the interpretation is the lab testing on these, quote, undisturbed samples showed a slightly dilative or phase transformational, which means it sort of contracts a little bit, then it dilates, whereas the CPT is indicating contractive. And of course, the uncertainty there is, are these samples truly undisturbed? And if they're sandy materials, and of course most tailings are often in that sandy, silty region, then we know that they're extremely sensitive to disturbance. And so even small changes in void ratio can change the material to being more dilative due to the densification that occurs during sampling. And so the times when I've seen that is typically where people have done lab testing on, quote, undisturbed samples. And it's always a pity that they didn't do the shear wave velocity. If they'd measured seismic CPT, they measured shear wave velocity in the field, and then they were able to measure shear wave velocity on the samples, they could have at least used the shear wave velocity as another indicator of the quality of the samples to determine whether or not there was some disturbance. And using this sort of approach that we outlined here, where looking at the normalized shear wave velocity as a function of void ratio is a guide to do that, and that's what that paper in '95 talked about a little bit. I think that's it. I think maybe one more. There was one last question. Were tailings subjected to a leaching process? I thought someone was going to ask me that, and I wish Brian was here, because they irrigated it, but I can't recall whether or not the irrigation was for leaching purposes. And so I'll have to leave that one and say, my memory's a little fuzzy on this. This project was a few years ago. And so I focused on the bits that we've talked about here, so hence I'm a little fuzzy on that one. So I'll pass that one, and maybe I'll ask Brian and get him to confirm it for me, and I can post it on the website. So hopefully you found that interesting. I'm planning to do a couple more webinars, all of which will focus predominantly on sort of case histories or the application side. The next one will be about the effect of high overburden pressures on the behavior of sandy soils. And so one could argue that's not directly related to CPT, but it's sort of this big issue for tailings, that these tailings are getting, impoundments are getting very large, and so what's the effect of high overburden pressure? So I'm giving this talk in Vancouver at the performance-based earthquake design conference in Vancouver in mid-July. And so after I give the talk there, I'll give a slightly longer version as a webinar, and we can discuss that. And there's a few more case histories that in the fall, I'll do a few more webinars that are built around case histories. So thank you for joining us. And as Kelly said, by about tomorrow, we'll have the recording of this webinar up on the website. So those of you that may have missed it will have the opportunity to watch the recording, or those of you that maybe want to rehear bits of it, you can always look at the other ones. So once again, thank you for attending, and hopefully you found it of interest and value. Thank you.